video about skill 2, which is about velocity graphs and force models. Our job is to analyze velocity graphs and predict crash force on a person or some object. So if we go to the Pear Deck that you had the link for, our real objective in this practice is to analyze velocity graphs and predict crash force on a sensor cart, because that allows us to actually compare the crash force that we predict to the sensor cart measurement, so we can learn something from that comparison. So open this Pear Deck and make sure that you're working along with me. I'm not going to actually finish the work here, so you'll need to finish it in Pear Deck. This is what we're trying to do. We have this equation, which is the same as the braking time equation, but sort of rearranged so that force is by itself. And we want to use this equation to make a prediction of force. But the only information that we have is information about change in velocity and change in time. So let's look at, like, for a velocity graph like this one, how is that going to be possible? On the actual bus collision test, you have velocity graphs that look a little bit different, but the idea is the same. We have velocity. Here's the 0 axis is in the middle of the graph, and this is a time axis going along. So in this case, the 0 is like a little more obviously like in the center, top to bottom, but we have this time axis going left to right. So when we say what part of the graph is before the collision and what part is after, we're sort of, it's up to you how you actually do this, but I would say if I was like highlighting parts of the graph, this part of the graph is before and this part of the graph is after. It's a little kind of subjective, like there's some decision here. I might even go over to 1.6 just because it makes it easier to do question 3b, which is the more important one actually. And this is asking you to annotate the time interval during the collision. Basically, how long did the collision take? And let me try to do that. The collision seems to start when the velocity starts going down here, and then it lasts until the velocity gets constant again over here. So it starts at 1.4 and ends at 1.6. There is a value there, like between those two times. It's a subtraction problem to figure out what this time interval is. It's basically how much time the collision takes. 1.6 minus 1.4 will give you a value for the change in time. That is like the time interval. Remember, that allows us to calculate force, because one of the values we need to calculate force is this time interval for like how long the collision took. Similarly, if we look at the y-axis of this graph, this is telling us how fast the cart was going, and it also has a change. But because the change is, because the change is on the y-axis, the annotating is going to look a little different. It does start out here, and then it changes all the way to here or so. Again, like getting this exactly perfect is much less important than getting some idea that is basically valid. So we have a change from, I'll just write this as ugly as it can get. I'll make this size smaller. 0.8 in the positive direction down to negative 0. This looks like it's around like 0.5. So the total change from 0.8 in the positive direction to the right to 0.5 in the negative direction is how much this graph goes down. And you can do this as a subtraction problem. You can also just sort of count boxes: 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.3. This, either one works. but you need to be thinking about the change from the initial value to the value afterwards, and that gives us a change in velocity. So once you have those two values from question 3 and question 4, then you can type into the general equation. So in general, part of skill 2 is going to involve using a general equation and then substituting and solving with values that you figured out from the graph in this case. So you can do that in the pear deck here. You can just say, okay, that equals the mass of whatever it is, which is 0.6 times whatever you got for the delta V, that is the change in velocity, divided by this. And then you can get a value for force. This does go on to some other questions. We need to, if we want to think about actual collisions, we need to look at data for actual collisions. So on the bus collision, there's this, which is about like what does this force actually look like? If we're calculating an average force with this equation, how does the actual force compare to that average force over time? Question 7 gets into some really tough details of this. If you're not able to do question 7, that's okay. But you should stop and think about question 6A, B, and C, because that's going to be important for us thinking about driver safety going forward.